1970, Baikonur Cosmodrome. A Proton K rocket sits on the pad carrying Venera 7, the third serious Soviet attempt to land a functioning spacecraft on Venus. The first two never made it past the atmosphere. One was crushed, the other went silent. The engineers who built the third one knew exactly what killed the first two, and they redesigned the pressure vessel from scratch. Thicker titanium walls, fewer seals, a simpler instrument package, because every component is a potential failure point. And on Venus, you don't get a second chance. The launch goes well, 7 months of cruise, then the descent. And for 35 minutes, the signal is a mess, weak, garbled, almost unreadable. Most of the team thinks it's another failure. It wasn't. Months later, a Soviet radio astronomer named Oleg Razhiga goes back through the raw data tapes with better processing. And buried in the noise, there's a signal, faint but real. The Venera 7 transmitted from the surface of Venus for about 23 minutes. The first human-made object to transmit data from another planet's surface. The data said 475 degrees Celsius, 90 atmospheres of pressure. Nobody celebrated. The mission was officially a partial success. They published the full data, including the 35 minutes of garbled signal, including the near loss, including the parts that didn't work, and then they started building the next one. That approach, build, fail, publish the failure, rebuild, defines the entire Venera program. And it's worth understanding why. Venus is not what most people think it is. For decades, science fiction imagined it as Earth's twin, warm, wet, maybe a jungle planet. It isn't. Venus is what happens when a greenhouse effect runs to its logical conclusion. The surface temperature is about 462 degrees Celsius. That's hotter than Mercury, which is closer to the Sun. The atmospheric pressure at the surface is around 90 times Earth's, equivalent to being roughly 900 meters underwater. The atmosphere is 96% carbon dioxide, with clouds of sulfuric acid. Nothing survives on the surface of Venus for long. Not rock formations, not geology as we understand it. The surface is periodically resurfaced by global volcanic events, and certainly not spacecraft. The engineering challenge is worth spelling out because it's easy to understate. At 462 degrees, lead melts, zinc melts, tin melts, standard electronics fail catastrophically, semiconductors stop functioning well above 200 degrees, solder joints dissolve, lubricants evaporate, seals soften and fail, and the pressure, 90 atmospheres, means the spacecraft needs to be a pressure vessel rated higher than a deep-sea submersible. And it all has to get there. 7 months of interplanetary cruise, a ballistic entry into an atmosphere thicker than anything in the solar system except the gas giants, and a landing on a surface you can't see through the clouds. With 1960s technology, without GPS, without real-time communication, the signal delay to Venus varies between about 2 and 14 minutes, depending on orbital position. The Soviet approach was direct. Build something, send it, see what breaks, fix it, send the next one. Venera 4, 1967. The spacecraft entered Venus's atmosphere and transmitted data during descent, temperature, pressure, chemical composition. It was the first probe to return data from another planet's atmosphere. The data was excellent, then the signal stopped. The probe was crushed at roughly 25 kilometers above the surface. The engineers had designed for 25 atmospheres. The actual atmosphere at that altitude was already beyond that. They had underestimated Venus, not by a small margin. Venera 5 and 6, 1969. Both upgraded to withstand 27 atmospheres. Both were crushed before reaching the surface, at around 20 kilometers altitude. The atmosphere was denser than the models predicted. Each failure returned better data. Each dataset improved the next design. The pattern is worth noticing. These weren't mysterious failures. They weren't hidden. After each mission, the Soviet scientific establishment published detailed technical papers with the full descent data, including exactly where and how the probe failed. The international planetary science community could see everything: what worked, what didn't, and what the data implied about the next attempt. Compare that to the way failure gets managed today. A spacecraft anomaly becomes a learning experience. A timeline slip becomes schedule optimization. A budget overrun gets absorbed into the next fiscal year without a public accounting. The Venera engineers lived in a different informational universe, not because they were more virtuous, but because the institutional incentive was different. Publication of results, including negative results, was the metric, not a press release, not shareholder confidence. The Venera 7, 1970, the one that barely worked. Redesigned pressure vessel, titanium, rated for 180 atmospheres, twice what they expected to encounter. The instrument package stripped down to the minimum: temperature sensor, pressure sensor, radio transmitter. The philosophy was, survive first, do science second. It survived, barely. That 23-minute signal from the surface, pulled out of noise months later, was the first data ever transmitted from the surface of another planet. The temperature reading, 475 degrees, later revised to around 465, and the pressure, approximately 90 atmospheres, became the foundational measurements for everything that followed. Venera 8, 1972, better landing, stronger signal. Added a photometer that showed the surface wasn't completely dark, enough sunlight filtered through the clouds for photography. This data point changed the next decade of mission design. If there was light, cameras could work. And then the program hit its stride. Venera 9 and 10, 1975, the first images from another planet's surface. Black and white, low resolution by modern standards, but the impact was seismic. Sharp-edged rocks, no erosion patterns consistent with wind, a landscape that looked freshly formed, because on Venus, the surface gets periodically recycled by volcanism. The engineering to get those images was remarkable. The camera had to function at 462 degrees and 90 atmospheres. The lens needed to survive sulfuric acid clouds during descent. The electronics needed to work long enough to scan, process, and transmit an image through an atmosphere that attenuates radio signals aggressively. The solution was a spring-loaded lens cap, a panoramic scanning camera with very few moving parts, and a transmission protocol that sent the image line by line. So even if the probe died mid-scan, you'd have partial data. Practical engineering, not elegant, effective. Venera 13, March 1st, 1982. The culmination of everything the program learned in 20 years. The lander reached the surface and transmitted for 127 minutes, over 2 hours, in an environment that should destroy any machine within an hour. 127 minutes of data. The kind of data set that keeps HALE staring at a screen past midnight. The first color photographs from another planet's surface. Orange-brown rocks under a thick, diffuse, yellowish sky. A landscape that looked alien in a way that Mars never quite manages. Mars looks like a desert, but Venus looked like nothing on Earth. The color calibration strip visible in the image. They included a test card so future scientists could verify the color accuracy. An engineering detail that tells you everything about the mentality. We might not be here to explain the data, so the data needs to explain itself. The probe also carried a microphone. It recorded the sound of Venus, wind, or atmospheric movement, or whatever you call it at 90 atmospheres. And it deployed a spring-loaded arm that sampled the soil, pulled it into an X-ray fluorescence chamber inside the pressure vessel, and analyzed the chemical composition of the surface, all within the 2-hour survival window. The results showed basaltic rock, similar to volcanic rock on Earth, another data point that nobody expected, and that shaped Venus models for the next 40 years. 13 missions to Venus, 7 failures of various degrees, 6 that returned data from the surface. Combined operating time on the surface, less than a full workday. And from those hours, patched together from multiple landers across a decade, came almost everything we know about Venus's surface from direct measurement. Nobody has been back since. The last surface mission was Vega 2 in 1985, 41 years ago. We have sent rovers to Mars that operate for years. We have satellites orbiting every major body in the inner solar system. But nobody has put a working instrument on the surface of Venus since the Soviets did it with titanium pressure vessels and analog electronics. There are reasons. Venus is harder than Mars. The engineering challenges haven't gotten easier, they've gotten better understood, which is not the same thing. A modern Venus lander would need high-temperature electronics that are still mostly experimental. The mission cost is high, the operating window is short, and the science case competes with Mars in every budget cycle. But there's another reason. And it's less comfortable. The Venera program worked because the engineers were allowed to fail publicly, learn publicly, and iterate fast. 13 missions in 20 years. 7 failures that were documented and studied, not explained away. The institutional structure rewarded data, even negative data. That culture is harder to find now. Not impossible, not extinct, but rarer. A failed mission today carries reputational risk that a Venera failure in 1967 didn't, because the audience was different, the accountability structure was different, and the media environment was different. The Venera program didn't succeed because Soviet engineers were better. It succeeded because they were allowed to be wrong, and the system around them treated being wrong as information rather than failure. Build, test, publish, iterate. The simplest engineering loop there is, and somehow the hardest to protect. 462 degrees, 90 atmospheres, 127 minutes. 3 numbers that represent not just a scientific achievement, but a way of doing things that we've struggled to maintain. Not because we forgot how, because the incentives shifted. The Venera engineers solved the problem of Venus with technology from the 1970s. The problem we haven't solved is the one they never had to face: how to build a system that tolerates failure as openly as they did. And that's a question that echoes past Venus. Because right now, orbiting above our own planet, there are roughly 36,000 tracked objects. Most of them aren't functional, they're debris. And the system that's supposed to deal with that problem looks nothing like the Venera program, and that might be exactly why it's not working.